types of schedulers. So long-term scheduler, short-term scheduler, and a mid-term scheduler. So the main goal of this short-term scheduler is moving these processes from the ready state to running state. So at a time, number of processes can be ready for execution. So all those process will be in ready state, and based upon the scheduling algorithm, that means the short-term scheduler or a dispatcher, so we have to pick up one process among the several, and that process will be allocated to the CPU for its execution. So that is the short-term scheduler. So first in this session, let us see the scheduling criteria, and then we will go for different algorithms. So for this scheduling these processes to CPU, that means allocating these processes to CPU, there are different scheduling algorithms. So based upon the criteria, we have to select one among different algorithms, right? So in this session, let us see the scheduling criteria, and then we will move on to the algorithms, scheduling algorithms. So scheduling criteria, the first criteria is CPU utilization. So the name itself indicates CPU utilization. CPU is a processor, right? So every process will be executed by this CPU. So we have to allocate this CPU to each process to get execution. So CPU utilization means how long the CPU is being busy. So CPU is busy means some processor running by the CPU, right? So how long CPU is busy. So busy means some process is going on execution. The second criteria is throughput. So as I said, that number of processes will be in ready state, and at a time each process will be given to the CPU. So this throughput means the number of processes executed in unit time. In particular time period, the number of processes being executed by the CPU, that is called a throughput. Next, turnaround time. Turnaround time. So this turnaround time means, so how much time the process takes to complete its execution, right? So the completion of time minus the start time. So the difference of beginning of the process and ending of the process. So how much time it takes for execution. Time taken for execution. That means difference of end time minus arrival time or beginning time, right? Next, waiting time. So how much time the process waits for getting the CPU. So even the process is in ready state, so there will be, if one process is going on execution by the CPU, then the second process should wait until the executing process completes its execution, right? So how much time the process waits for allocation of this CPU. Right. Time waited by the process to get the CPU. Next, response time. See here, response time means after starting, that means after beginning of execution, the time taken to get the first response by the CPU, that is called the response time. after beginning of execution, time to get first response is called response time. So these are the different scheduling criteria. Scheduling criteria, right? CPU utilization, throughput, turnaround time, waiting time, and the response time. So for every process, we can calculate all these things. So except this CPU utilization, right? So the CPU utilization means how long the CPU is busy. Throughput means the number of processes executed in given time period at a unit time. Turnaround time is time taken for execution. That means the difference of completion time and arrival time. And the waiting time. Waiting time means time waited by the processor to get the CPU, right? So response time, after beginning of execution, time to get the first response by the CPU. This is called the response time. So all these are the different scheduling criteria. So this will be taken care by the short-term scheduler, right? So short-term scheduler main task is, so by using the scheduling algorithms, process will be moved from ready to running state. That means process will be allocated to the CPU, or CPU is allocated to the process. Friends, welcome back to our channel. Right. So now we will see the different scheduling algorithms to schedule the process. That means to move the process from ready state to running state. So as we have discussed earlier, there is a ready state, so which contains a number of processes, and at a time only one process can be allocated to the CPU. So this selection of the process is done by the scheduler, right? And this selection will be done by using some scheduling algorithms. So based upon these scheduling algorithms, we have to select one among those different there are different scheduling algorithms. So based upon the scheduling algorithm, the scheduler will schedule the process to the CPU. That means allocates this process to the processor for its execution. Right? Now let us see the scheduling algorithms one by one. So in today's class, let us see the one scheduling algorithm, that is called the first scheduling algorithm, Fcfs. That means first come, first serve. First come, first serve. So the name itself indicates whatever the process first arrived in the ready state, that process will be allocated to the CPU. So until that process is executed, no other process will be moved from the ready state to running state. So all the remaining process should be in a wait until the process gets executed. Right? Now, so there are two different modes while performing this scheduling. That is, two modes. One is non-preemptive, another one is preemptive. So here non-preemptive means no interruption. So there will be no interruption to the execution until it completes its execution. Preemptive, there will be interruption. So if any high priority, if any process with a high priority is available, then automatically the process which is going to be executed in the CPU will be get back, and the high priority process will be sent to the CPU. So that will be done in preemptive mode. right? So we can select any one in this non-preemptive or preemptive. Either if it is a non-preemptive, it's a no interruption. There will be no interruption. That means if one process is going to be executed by the CPU, then all the remaining process should be wait until it completes its execution by the CPU. So once it gets completed, then only the second process will be allocated to the CPU. Now, let us see the Fcfs, the first come first serve. First come first serve. So here we are using the mode, say non-preemptive, right? And criteria is arrival time. So based upon the arrival time, we will schedule the process. So that's what we are saying. Which process gets first enter into the ready state, that process will be allocated to the CPU. That is called arrival time, right? Right. Let us take an example so that your doubt will be clarified, right? So if there are four processes. So four processes with the four IDs P1, P2, P3 and P4, and the arrival time is 0, 1, 2, 3. So 0, 1, 2, 3 is the arrival time. Let us take it is a relative time. Okay, it's not an absolute time, it's a relative time. So 0 means this process has been entered into ready state. 1 means next this process has been entered into ready state. Let us take it as a milliseconds or seconds or hours, whatever it may be, right? So it's a time, arrival time. Next, burst time. So this is the arrival time, this is the burst time. So what is a burst time? Burst time means the time required to complete its execution. So process P1 has entered at 0 milliseconds into the ready state, and it requires 5 milliseconds to complete its execution. Next, P2 arrives at 1 millisecond and it requires 3 milliseconds to complete its execution, right? So generally in the problems, so we are supposed to find average waiting time and average turnaround time, right? So these two questions will be frequently asked, that is, so they will give a processes, arrival time and the burst time, and we are supposed to calculate this average waiting time and average turnaround time. So before going to calculate this one, first we have to calculate this waiting time and the turnaround time, right? See, for this let us draw the Gantt chart. This is called a Gantt chart. Gantt chart is the execution of the process step by step. See, I will show you. So always the process starts from the 0th milliseconds. So 0, at the time 0, process 1 enters into the ready state. So process 1 will be executed. P1 will be executed. So how much time it requires to complete its execution? 5 milliseconds. So until 5, P1 will be get executed. Now see, the time is 5 milliseconds. At the time of 5, all the remaining 3 processes are available, right? So at the time 0, only one process is available in ready state. So automatically this process is allocated to the CPU and CPU executes this process. So it takes 5 milliseconds to complete its execution, right? So after executing this process, it requires a 5 milliseconds. So now the time is 5 milliseconds. At the time of 5, there are 3 processes waiting for the CPU in the ready queue, right? So P2 arrival time is 1, P3 arrival time is 2, and P4 arrival time is 3. So after completion of P1, 3 processes are available. So which process we have to consider? So based upon the arrival time, that means first come first serve. Which comes first into the ready queue, that process should be allocated to the CPU. So among these, 1, arrival time is 1. So P2 comes after P1, right? So P2 will be given to the CPU and it takes 3 milliseconds to complete its execution. So P2 starts from 5 and it requires 3, so it completes at 8 milliseconds. Now 2 more processes are there, so P3, so arrival time, we have to go for arrival time. So arrival time for P3 is 2, arrival time for P4 is 3. So P3 enters into the ready queue before P4, right? So P3 should be allocated to the CPU. So P3, right? So it enters in 8 milliseconds and it requires some 8 milliseconds. So at 16 milliseconds P3 gets completed. Now P4. So P4 enters into the queue. So it requires 22 milliseconds to complete the P4. Hope you understood. So this is the queue. This is the CPU, allocation of the CPU. So first P1, arrival time 0. So at the 0, P1 enter into the ready queue. So P1 is allocated to the CPU and CPU executes till 5 milliseconds. And the time of 5, there are 3 processes available in ready queue. So among these 3, we have to select only one. That is based upon the first come first serve. P2, among these 3, P2 comes first into the ready queue according to the arrival time. So P2 is allocated to the CPU. It takes 3 milliseconds. So 5 plus 3, 8. So again, next P3 is given to the CPU after completion of P2 and it takes 8 milliseconds. So 16, complete 16. And P4 is allocated to the CPU. It takes total 6 milliseconds. Right? So one thing we can observe. So if you add all these burst time, that is equal to the total time required to complete all the processes, right? So this is 22, 5, 3, 8, 8 plus 8, 16, 16 plus 6, 22. Now let us write the completion time. So completion time for each process. So when the P1 is completed, so here P1 starting time is 0, completed at 5. So P1 completed at 5. P2, what about P2? Arrived at 1 but waited for some time. It arrived at 5 and completed at 8. So completion time of P2 is 8. Completion of P3 16. Completion of P4 22. This is the completion time. Now turn around time. What is the turn around time for all the processes? See, turn around time, as I have said in the previous one, in the scheduling criteria, turn around time is the difference between end time and start time. So completion time minus arrival time. Completion time minus arrival time. So I will write above. Turn around time, it's a completion time minus arrival time. So end time minus starting time. So 5 minus 0, turn around time is 5. 8 minus 1, it is 7. 16 minus 2, it's a 14. 22 minus 3, it's a 19. So turn around time for each process is 5, 7, 14 and 19. Next, waiting time. So how much time it is waited? Waiting time. So waiting time means whenever the so how much time the process waits to get the CPU, right? So how much time the process is waiting to get the CPU. So it arrived at 0, right? So it arrives at coming to this process P1, it arrived at 0 and the CPU is allocated at 0. So automatically, see, simply we can say turnaround time minus burst time. Minus burst time. Or I will explain you. So arrived at 0, CPU allocated at 0. So it is 0. So according to the formula, turnaround time minus burst time, 5 minus 5, 0. Second process, coming to the second process. He arrived at 1 and allocated to the CPU at 5, right? P2 is allocated at 5, it arrived at 1. So 5 minus 1. So that means 4. 4 milliseconds the P2 has waited. So according to the formula, 7 minus 3, it's 4. Next, P3 arrived at 2 and CPU is allocated at 8. So 8 minus 2, 6. So here 14 minus 8, 6. Next, P4 arrived at 3 and here CPU is allocated at 16. So 16 minus 3, 13. So hope you understood. So P1 is arrived at 0. Here the CPU is allocated at 0. So automatically there is no waiting time. Next, P2 is arrived at 1 and CPU is allocated at 5. So 5 minus 1, 4. P3 is arrived at 2 and allocated at 8. 8 minus 2, 6. P4 is arrived at 3, allocated at 16. 16 minus 3, so 13. Right? Hope you understood this simple thing. So for getting this average turnaround time, average all these things, so total turnaround time is 5 plus 7, 12, 12 plus 14, 26, 26 plus 19 is 45. Divided by, okay. So average turnaround time is equal to total turnaround time divided by number of processes. That is 4. 11.2 something. Right? Next, coming to the waiting time. So total waiting time. 0 plus 4. 0 plus 4, 4, 4 plus 6, 10, 10 plus 13, 23. Similarly, average waiting time is equal to total waiting time divided by number of processes. So, .7 milliseconds around. So hope you understood this. Is a simple example how to calculate or how to schedule the process by using first come first serve. So this is the mode where we have calculated is non-preemptive, and one more thing, this is based upon the arrival time, right? So mode non-preemptive and arrival time, based upon the arrival time, will send one process at a time to the CPU. So there will be no interruption at all. So until the process gets executed by the CPU, the next process should be in a ready state itself. Right. So let us take one more example. So here also there are 4 processes, P1, P2, P3, P4, and arrival time 1, 2, 3, 4, and the burst time, that is the time to be executed for this processor, 10, 5, 7 and 6. Now let us see for this example. Again we have to prepare the Gantt chart, right? Gantt chart, the CPU allocation. So as I have said, the CPU starts always from 0. So the first process arrived at 1 milliseconds. So from 0 to 1 the CPU will be in idle state. Alright. So the CPU will be idle state from 0 to 1. So at the time of 1, P1 will be allocated to the CPU. So it takes 10 milliseconds to complete its execution. So it takes some 10 milliseconds. So 1 plus 10, it will be 11. Right? So next. So after completion of P2 and P1, P2 is arrived at 2. So at the time of 11, all these 3 processes are available in the ready queue. So based upon the arrival time, P2 is first. So P2 will be executed next. So what is the time of P2? 5. So 11 plus 5, it takes 16. That means the completion time of P2 is 16. So next P3 will be get executed. So it requires 7. So 23. And P4, it requires 6. It requires 29. Right? So from 0 to 1 the CPU will be in idle state. CPU will be in idle state because the process enter into the ready queue from 1 millisecond itself, right? So here now the completion time, what is the completion time? The completion of P1 is 11, completion of P2 is 16, the completion of P3 is 23, the completion of P4 is 29, right? Next, turnaround time, the completion time minus arrival time. So 11 minus 1 is 10, 16 minus 2 it's 14, 23 minus 3 is 20, 29 minus 4 it's 25. So this is the turnaround time and the waiting time. So coming to the waiting time, it arrived at 1, the CPU is allocated at 1. So obviously it will be 0. So turnaround time minus burst time. Arrived at 2, here started at 11, right? 11 minus 2 it's 9. So 14 minus 5 it's 9. Next, arrived at 3 and started at 16. 16 minus 3 it's 13. So 20 minus 7 it's 13. Next, P4 arrived at 4, started at 23. So CPU is allocated at 23. 23 minus 4 is 19. Right? So this is the simple thing. Now find out the total turnaround time. So total turnaround time is 10 plus 14, 24, 44 and 69. 24, 44 and 69, right? Average total time, so that is 69 by 4. Similarly, total waiting time, 0 plus 9, 9, 9 plus 13, 22, 22 plus 19, it's a 41. Similarly, average waiting time is 41 by 4. Right? This is one more example for first come first serve. So here, it's not a mandatory that every process is arrived at 0 milliseconds, right? So based upon the arrival time, we have to prepare the Gantt chart. So for that purpose, I have given this example. Now let us take one more example with a different case, right? So I am explaining with the different cases so that you can solve any type of problem regarding this FCFS, first come first serve scheduling algorithm, right? So now let us see the third case. Again, consider the four processes P1, P2, P3 and P4. So arrival time is 0, 3, 5 and 7. Now the completion time is, the execution time for each process required by each process is 2, 1, 2, 3. Now prepare the Gantt chart. See, again here the P1 starts from 0, so automatically at the 0 milliseconds P1 is executed, right? So it takes 2 milliseconds, so till 2 it get executed, and the second process is arrived at 3. Now CPU is still in waiting state, so CPU is waiting for process, right? So here process is not waiting for CPU, CPU is waiting for the process. Now from the 2 to 3, the CPU will be in idle state. CPU is in idle state. At the time 3, P2 arrived. So P2 is given to the CPU. So it requires only 1 millisecond. So at the time of 4, it completes its execution. P3 again arrived at 5. So from 4 to 5 again the CPU is in idle state. So in this example, the CPU is waiting for processors. So in the previous two examples, the processors are waiting for CPU. Right? Next, so from 4 to 5, the CPU is in idle. At the time of 5, P3 arrived. So P3 will be executed. So it takes 2. So 7. At the time of 7, P4 arrived. So immediately P4 will be given to the CPU. So total it takes some 10 milliseconds to complete the process P4. Right? Hope you understood this one. So it arrived at 0, it takes 2 milliseconds. So 0, from 0 to 2, P1 is executed, by the CPU, and the P2 is arrived at 3rd millisecond. So from 2 to 3, the CPU will be in idle state, and at the 3, P2 arrived. So it takes only 1 milliseconds to execute this process. So P2 is executed from 3 to 4, and again P3 arrived at 5. So from 4 to 5, again the CPU is in idle state. So no process is ready for execution. So from at the 5, P3 is allotted to the CPU, and CPU executes this P3 till 7 milliseconds. So at the time of 7, P4 is arrived, so P4 executes till 10. So now completion time. So what is the completion time of P1? 2. At the time of 2, P1 completed. P2, 4. At the time of 4, P2 completed. P3, 7. At the time of 7, P3 completed. P4, at the time of 10, P4 completed. Right? So next, turnaround time. So completion time minus arrival time. 2, 4 minus 3, 1, 7 minus 5, 2, 10 minus 7, 3. Waiting time. See, P1 arrived at 0, CPU is allocated at 0. So 2 minus 2. Next, P2 arrived at 3, CPU is allotted at 3. Again it's 0. So 1 minus 1. Next, P3. So arrived at 5, CPU is allocated at 5. Okay, P3 starting time is 5. Arrived at 5. So 0. P4 arrived at 7. Starting time of P4 is 7. So 7, 0. See, if you see this formula, turnaround time minus burst time, 2 minus 2, 0, 1 minus 1, 0, 2 minus 2, 0, 3 minus 3, 0. Okay, so in this example, the CPU is waiting for the processes. No process is waiting for the CPU. Right? This is another case. Now calculate the turnaround time. This is the turnaround time. 2 plus 2, 4, 5, 8. So 8. So 8 by 2. Here waiting time is 0. No process in a waiting state to get the CPU. So this is one more example for the first come first serve. So hope you understood these different cases. So based upon the arrival time, we have to prepare the Gantt chart, and from the Gantt chart we have to write the completion time, turnaround time and waiting time. Turnaround time, I am writing the formula. Turnaround time, as we said that it's a time between starting and ending. So completion time minus arrival time. Completion time minus arrival time. Similarly, waiting time. So by seeing this Gantt chart, we can write the waiting time, or directly we can use the formula turnaround time minus completion time. Burst time. Turnaround time minus burst time. So by using this formula, you can calculate the turnaround time and waiting time, so that we can calculate the average waiting time and average turnaround time. So once again I am saying this is a non-preemptive mode, so no interruption will be there. Even though there is a process with highest priority, it should wait till the process completes execution by the CPU. Right? So only the scheduler will schedule the processes based upon the arrival time. The process will be get allocated to the CPU. So hope you understood this simple scheduling algorithm. Shortest job first. That means the process which is having the less execution time which requires the less execution time, that we call it as a shortest job. So in the previous session we have discussed the scheduling criteria, that is the CPU utilization, throughput, turnaround time, and waiting time and response time. So in them we have seen the one of the scheduling algorithm, that is Fcfs, first come first serve. That means which arrives first into the ready queue, so that process will be allocated to the memory. So after completion of that process, based upon the arrival time, the second process will be allocated to the processor, CPU. So that happens in the first come first serve. So coming to this shortest job first, based upon the execution time, we will schedule the process to the CPU. So here this can be implemented in two modes. One is preemption and non-preemption. So we have discussed in the previous session, that is if it is a non-preemption, there will be no interruption. If one process is allocated to the CPU, so until the process being executed completes its execution, no other process will be allocated to the CPU. So that is called non-preemptive mode. And coming to the preemptive mode, if any process with the highest priority is there, automatically the already executing process will be sent back to the ready state, and this highest priority process will be allocated to the CPU. So that is a preemption. Now let us look on the first case, that is non-preemption, SJF. So here we are applying mode is non-preemptive. So non-preemptive means no interruption. And the criteria is burst time, right? The criteria is burst time. So in the Fcfs, the criteria is arrival time. Now let us see an example. So here also the frequent asked question is to calculate the average turnaround time and average waiting time, right, by using SJF with non-preemption mode. Now let us take the process. So here I have taken total 5 processes. The arrival time 0, 1, 2, 3, 4. So again this arrival time is a relative. It's not an absolute. It's a relative. That means lower the number, it comes the processor. The processor enters into the ready queue, right? The order of a process enters into the ready queue. Next, this is the burst time. This is the arrival time, right? So for this we have to prepare the Gantt chart. So let us prepare the Gantt chart. So always starts from the 0. So at the time 0, P1 arrived. So here among all these 5 processes, which process is having a very lower time to execute itself is P2. But P2 arrives at 1 millisecond, right? At 0, P1 arrived. That means at the time 0 in the ready queue, only one process is available, so automatically that process will be allocated to the CPU. So P1. So this will execute it until 8 milliseconds. So when the time is 8, all the remaining processes are ready in the ready queue, entered into the ready queue. So among all these processes, so P2, P3, P4, P5, which one is having the lowest burst time? 4. That means P2 is having the lowest burst time, so P2 will be given to the CPU. So 4, so at 12. So again, this completed, this completed. Now there are 3 processes available in the ready state. Among them, P4 is having the lowest burst time. So the next process is P4 is allocated to the CPU. So P4 with 5, so it's a 17. P4. Next, 2 processes are in the ready queue. Among these 2 processes, P5 is having the shortest burst time. So P5 is allocated to CPU. So it will be executed till 23, right? So P5. Next, only one process is available in the ready queue. Automatically P3 will be allocated to the CPU and P3 will be allocated till 32. Now count this one: 12, 21, 26, 32, right? 32. Total completion of for all, total time required to complete all these processes is 8 plus 4, 12, 12 plus 9, 21, 21 plus 5, 26 plus 6, 32. So 32 milliseconds is required to complete all the processes, right? Now, what is the completion time? The time required for completion. So P1 is completed at 8, P2 is completed at 12, P3 is completed at 32, P4 is completed at 17, P5 is completed at 23. Next, turnaround time. What is the turnaround time? So as we know that turnaround time is completion time minus arrival time. So turnaround time is equal to completion time minus arrival time. See, completion time minus arrival time: 8, 12 minus 1, 11, 32 minus 2, 30, 17 minus 3, 14, 23 minus 4, 19. Right? Now, so waiting time. What is the waiting time? How much time the process is waited for the CPU, right? So the waiting time is equal to turnaround time minus burst time. The formula is turnaround time minus burst time, or you can simply use this Gantt chart for completion. So P1 arrived at 0, arrival time 0, so automatically 0. Next, P2, the CPU is allocated at 8 and it arrived at 1, so 8 minus 1, 7. So if you apply the formula, you will get the same thing: 8 minus 8, 0, 11 minus 4, 7. Next, P3, so allocated the CPU at 23 and arrived at 2, so 23 minus 2, 21. So if you apply the formula, 30 minus 9, 21. Next, P4, allocated the CPU at 12, arrived at 3, 12 minus 3, it's 9. 14 minus 5, it's 9. P5, allocated the memory at 17, arrived at 4, so 17 minus 4, it's 13. It's 13. Hope you understood this, right? After getting this, we can calculate the average turnaround time. So total turnaround time is equal to, so 8 plus 11, 19, 19 plus 30, 49, 49 plus 14, 63, 63 plus 19, 82, right? Next, similarly, average turnaround time is equal to 82 divided by how many processes? 5 processes divided by 5. Similarly, total waiting time is equal to 0 plus 7, 7, 7 plus 21, 28, 28 plus 9, 37, 37 plus 13, 50. So 50, so average waiting time is equal to 50 by 5. So this is a simple thing. So here the process is allocated to the CPU based upon the burst time. So initially at the time 0, no other process entered into the ready. So even though the burst time is higher for the process P1, P1 is allocated to the CPU. So after completion of P1, as it is a non-preemption, so once the process is allocated to the CPU, we should not disturb it until it gets execution. So it completes its execution. Now at the time 8, all the 4 processes are available in the ready queue. So among the 4, so select the shortest job. That means the shortest burst time. So among those, we are having P2 having the shortest job. So P2 get executed. So at the time 12, remaining 3 are available. So among these 3 processes, P5 is having the lower burst time. So P4 is allocated to the CPU, and then P5 is allocated, and then P3 is allocated, and the remaining process is same. So as it is a non-preemption, we should not disturb the processes until it gets executed. So if it's a preemption, then based upon the highest priority, we will just shift back the process to the ready state, and we will assign the CPU to the highest priority process, right? So as it is a non-preemption, we should not disturb these processes, the execution of the processes. So hope you understood. Now let us see one more example and we will wind up this concept, right? So second one, we will consider the 4 processes. The times are, arrival time is 1, 2, 3 and 4, and the burst times are 1, 3, 6 and 2, right? So yes, this is the second example. Let us trace this one, or let us calculate this one. Let us take 21. Okay, so prepare the Gantt chart. So this is the Gantt chart. So at the time 0, not even a single process is available in the ready queue. So the CPU should be in idle state till 1. So CPU is in idle state till 1. So at the time 1, we are having only one process enters into the ready queue, that is P1. So P1 is allocated here. So total the time executed by the P1 is 21. So 22. As we have started at the 1 millisecond. So at the 22nd millisecond, P1 is completed. So at this time, 3 processes are available in the ready queue. So among these 3, P4 is having the shortest job. So P4 is allocated to the CPU. So P4 is allocated, so 24, right? 24. Now, at the time 24, 2 processes are available in the CPU. So among these 2 processes, P2 is having the lowest burst time. So P2 will be allocated here. So time is 3, so it takes 27. Till 27, the P2 will be executed. So after that, only one process is remaining in the ready queue, that is P3. Now P3 is available, so P3 will be allocated and will be completed till 33. So total time required to complete all these processes is 33. Now calculate this one, so you can get that. 21 plus 3, 24, 30, 32 and 1 is idle, so total 33. Right? Now, let us write the completion time. So P1 is completed at 22, P2 is completed at 27, P3 is completed at 33, P4 is completed at 24. Turnaround time. So turnaround time is equal to completion time minus arrival time. So 22 minus 1, 21, 27 minus 2, 25, 33 minus 3, 30, 24 minus 4, 20. Now waiting time. So how much time the process waits for the CPU. So waiting time is equal to turnaround time minus burst time. Right? Turnaround time minus burst time. 21 minus 21, 0. So here let us see that. So P1 enters into at 1. Right? P1 enters, that means P1 allocated the CPU at 1 millisecond, it arrived at 1. So there is no waiting time. And coming to the P2, P2 allocated to the CPU at 24 and arrived at 2. So 22. 25 minus 3, 22. Next, P3. P3, the CPU is allocated at time 27 and arrived at 3. 27 minus 3, so 24. So 30 minus 6, 24. So I am saying the 2 ways, right? So based upon the formula, we can write this waiting time, or by using this Gantt chart also we can find out the waiting time, right? Next, P4. So P4 enters into the CPU, assigned to the CPU at 22 and they arrived at 4. 22 minus 4, 18. So 20 minus 2, 18. So this is the waiting time for all these processes. So now total turnaround time 21 plus 25, it's a 46. 46 plus 30, 76. 76 plus 20, 96. The average turnaround time is 96 divided by 4. Waiting time 22, 46, 46 and 64. Waiting time, average waiting time is 64 by 4, as we have taken only 4 processes. So hope you understood this simple shortest job first. So here we have applied this in a non-preemption mode, that is no interruption while executing the process, and the criteria is burst time. So based upon the burst time, we have calculated or we have prepared this Gantt chart. We have scheduled the process to the CPU. So hope you understood this shortest job first. So SJF in a non-preemptive mode, that is shortest job first. So whatever the process having with a short execution time, that is a burst time, that process should be allocated to the CPU. So here in the previous session we have seen in a mode non-preemption, that is there will be no interruption during the execution of a process. So if one process is allocated to the CPU, until the process being executed, no other process should enter into the running state, right? So there will be no interruption. Now here in today's session we will see the preemption mode. Mode is a preemptive mode and the criteria is a burst time. So here there will be an interruption. So if one process is being executed by the CPU, so at the same time if any other process with lower burst time appears, automatically the executing process will be sent back to the ready state, and again this high priority process will be given to the CPU. So that is called a preemption, right? So let us take an example so that you can clearly understand this one. See, I will take an example. So let us take 5 processes: P1, P2, P3, P4, P5. The arrival time is 0, 1, 2, 3, 4, right? And the burst time is 8, 1, 3, 2, 6. So this is the burst time, this is the arrival time, right? First we have to prepare the Gantt chart. The procedure is same, right? The procedure is same. So we have to prepare Gantt chart. So the Gantt chart always starts from the time 0. So as I have said that the arrival time here is completely relative, it's not an absolute, right? So at the 0 time, here there are 5 processes, and P1 it requires 8 milliseconds to execute its process, P2 requires only 1 millisecond, P3 requires 3, P4 requires 2 and P5 requires 6. So our main problem is here mode is preemptive and criteria is burst time. So whatever the process which is having with low burst time should be executed first. So by observing this, P2 is having the lowest burst time among all these 5. So actually P2 should be allocated to the CPU, but P2 is arrived at 1. So at the time 0, only P1 is available in ready state. So P1 should be allocated. So as it is a preemptive, whenever the highest priority process arrives into a ready state, automatically the present process must be sent back to the ready and the highest priority should be executed. So after 1 second, so P2 has arrived into ready state, which is having low priority. So here one second has been executed. So now the P1 burst time is 7. Now the P1 burst time is 7, right? So after 1 millisecond, P2 arrived into the ready state. So there are two processes now in ready state, P1 and P2. Among that, which one is having the lowest burst time? P1 having the 7, P2 having 1. So P2 should be allocated to the CPU. So after that it becomes 0. That means executed. Now the CPU time, the time is 2. So P3 arrived into the ready state. P3 having 3, P1 is having 7. So which one among these two, which one is having the lowest? P3. So P3 is allocated to CPU. Right. Now, so after 1 second, 3 here, so this has been completed 1 second. Okay, P3 has executed in 1 second. So now P3 requires only 2 seconds to execute. So at the time 3, P4 arrived into the ready queue. So now P1 is available, P3 is available, and P4 is available. So P1 requires 7, P3 requires 2, P4 requires 2. Right? So here, if any two processes having the same burst time, then select the process which is having the lowest ID. Right? Lowest ID. So here P3 and P4 are having the lowest burst time. That means equal burst time, 2 and 2. So P3, P4, which is having the lowest ID, P3. So continue P3 till it executes the process. So 5. So until 5 it will be executed. So P3 completed. Now at the time 5, P4 is available in ready queue because it arrived at 3. P5 is available in ready queue because it arrived at 4. P1 is also available because it requires still 7 seconds to complete its execution. Now among these three, which one is having the lowest burst time? P4. So P4 is allocated to the CPU. So how much time? 2 seconds, so 7. P4 completed. Now P5 and P1 both are available in ready queue. So among these, P5 is having the lowest burst time. So P5 is allocated. So 13. Now only one is in ready queue, that is P1, which requires total 20. See, 8 plus 1, 9, 9 plus 3, 12, 14, 20. So the time required to complete execution of all the processes is 20. Okay, so hope you understood this one. Simple thing, don't get confused. So once again I will repeat the procedure. So first, at the arrival time 0, only one process is available in ready queue. So automatically P1 is allocated to CPU. So whenever the time changes to 1, at arrival time 1, P2 also available in CPU. As it is a preemption, whenever we receive the priority with lowest burst time, that process should be allocated to the CPU. So here P2 is arrived at 1 with a burst time 1. So 1 is less than 7. Here 7 because already 1 second completed here. 1 second of execution is completed by the process P1. So 8 becomes 7, right? So P1 still requires 7 seconds to complete its execution. So P2 will be having only one burst time. So P2 is allocated to CPU and it becomes 0. Now at the time of 2, P3 is available and P1 is available. Only P3 and P1 is available, right? So among these two, P3 is having the lowest burst time, that is 3. right? So P3 is given to the CPU. So after again completion of 1 second, then P3 requires 2 seconds to complete its execution, and at the arrival time 3, P4 is also available in ready queue, which requires the same 2 seconds to complete its execution. So here there are 2 processes which requires executing, which requires to execute the process is only 2 seconds. So if you get this case, select the process such that which is having the lowest process ID. So here P3, P4, P3 is having the lowest ID. So here I have given P3 is allocated to CPU, and CPU completes the process P3 at the time of 5. Now P5 is available, P4 is available, P1 is available. So among these 3, here 7 requires, P4 requires 2, P5 requires 6. P4 is having the lowest burst time, P4 is allocated to the CPU. Next, P5 is allocated to the CPU, and then P1 is allocated to the CPU. Hope you understood. So to avoid the confusion, you can write 2 terms. See, 2 to 3, that is P3. So in this here, P3 and P4 is having only the same burst times. So I have selected only P3, right? Now your confusion gets clear, right? Now let us write the completion time. Completion time. So P1 requires 20 seconds to complete. P2 requires 2 seconds to complete. So I will arrange all these things. Right. P3 requires 5 seconds to complete. P4 requires 7 seconds to complete. P5 requires 13 seconds to complete. Next, turnaround time. So turnaround time is completion time minus arrival time, right? 20 minus 0, 20. 2 minus 1, it's 1. 5 minus 2, it's 3. 7 minus 3, it's 4. 13 minus 4, it's 9. Right? Now, calculate the waiting time. Waiting time, that is turnaround time minus burst time. Right? See, 20 minus 8, it's 12. Next, 1 minus 1, it's 0. 3 minus 3, it's 0. 4 minus 2, it's 2. 9 minus 6, it's 3. Right? So that's the waiting time. In order to get the average turnaround time, so add all these things. So you will get the total. So 21, so 24, 28, 37. So total 37 divided by 5 process. This is the average waiting time. Sorry, average turnaround time. Average turnaround time. Now average waiting time. So 12 plus 2, 4. 14. 14 plus 3, 17 divided by 5. This is the average waiting time. Hope you understood this thing, right? Okay, so the same procedure you have to apply, but whenever the process with the lowest burst time arrived in the ready queue, immediately that process will be given to the CPU. So let us take one more example so that your doubt will be clarified. Let us take 4 processes now. Zero, 2, 4 and 5. Seven, 4, 1 and 4. Right? Now prepare the Gantt chart. So at the time of 0, so among all the 4 processes, this is the process which is having the lowest burst time. and these two processes are having the equal burst time, that is 4, and at last P1 is having the 7 milliseconds to complete its execution. Now, so at the time 0, only P1 is available in ready queue, so P1 will be allocated to the CPU. So until 2, the P1 is executed. So until 2, the P1 gets executed. So at the time of 2, P2 is available in, so here 7 becomes 5 because already 2 seconds have been completed by the P1. Here in P2 arrives into ready queue at the time 2. So at the time 2 with the lowest burst time. So at the time 2, P1 and P2 are available in ready queue. So P1 requires 5 seconds, P2 requires 4 seconds. So this one is the lowest among these two. So P2 will be get executed, right? So until arrival time 4. So at the time 4, P3, so here again 2, it reduces to 2 because P2 also executed 2 seconds. So at the time of 4, P3 is arrived in ready queue, which is having the lowest burst time 1. So now at the time of 4, P1 is available in ready queue, P2 is available in ready queue, and P3 is also available in ready queue. So P1 requires 5 milliseconds, P2 requires 2 milliseconds, P3 requires only 1 millisecond. So P3 is allocated to CPU and it finished its execution. So this finished its execution. This one completed. Now at the time of 5, P4 also available in ready queue. So P1, P2, P4, 3 processes are available in ready queue. So P1 requires 5, P2 requires 2, P4 requires 4. So among these, P2 requires 2. This is the lowest burst time. So now P2 is available, that means assigned to the CPU. This completed, P2 is completed. Now P1 and P4. P4 requires 4, P1 requires 5. So among these two, P4 is having the lowest burst time. So P4 is allocated to CPU and then P1 is allocated to CPU. Right? So total 16 milliseconds requires to complete all the processes to be get executed. Now let us check this one. 7 plus 4, 11. 11 plus 1, 12. 12 plus 4, 16. Total 16. So this Gantt chart is correct. I will erase all these things. Right? Now completion. The completion time. So P1 is completed at 16. P2 is completed at 7. P3 is completed at 5. P4 is completed at 11. So turnaround time is completion time minus arrival time. 16 minus 0 is 16. 7 minus 2 is 5. 5 minus 4 is 1. 11 minus 5 is 6. So waiting time. So waiting time means turnaround time minus burst time. So I will write here so that you can clearly get that. Turnaround time is equal to completion time minus arrival time. Similarly, waiting time is equal to turnaround time minus burst time. So this is a simple formula to fill the table, right? So turnaround time minus burst time. 16 minus 7, 9 seconds. 5 minus 4, 1 second. 1 plus 1 minus 1, 0. Right? So 6 minus 5, sorry, 6 minus 4, 2. Hope you understood this one, right? So the waiting time can be calculated by using this Gantt chart also, right? So anything is right. In the next session, we will move on to the another scheduling algorithm. So before closing that, so I am just repeating the same thing. So here we are using the preemptive mode, that is, if any process is with the lowest burst time appears in the ready queue, automatically that particular process will be allocated to the CPU. So already the executing process will be sent back to the ready state. Right? So from this we have to prepare the Gantt chart. From this Gantt chart we have to fill this completion time, turnaround time and waiting time. Now calculate the average turnaround time and average waiting time. 16 plus 5, 21, 22, 28 divided by 4. So this is the average turnaround time. Here 9 plus 1, 10, 10 plus 2, 12, 12 by 4. 12 by 4 is the average waiting time. Hope you understood this section. Let us have a look on one more scheduling algorithm, that is a priority scheduling algorithm. Priority scheduling algorithm. So for every process which is in a ready queue will be given some priority. So based upon that priority we have to allocate the process to CPU. So coming to this first come first serve, based upon the arrival time, so which process arrived first into the ready queue, that process will be get executed by the CPU. And then in the shortest job first, which is the which process is having the least burst time, so that process will be allocated to the CPU. And now in this priority scheduling, so some priorities will be given to the processes. So based upon that priority, the process will be allocated to the CPU. So here the priorities will be from 0 to 7 or some 0 to 4093, right? So that is some numbering. So numerical numbers will be given as a priority to the processes, right? See, let us see an example so that you will know the procedure. So priority for the processes, process ID, arrival time, burst time, completion time, turnaround time, waiting time. So we need to calculate all these things. So now let us take the process IDs. So that is from, I will take 5 processes, P1, P2, P3, P4 and P5. So total 5 processes, and the arrival time for this process are 0, 1, 2, 3 and 4. So arrival time, as I said that arrival time is a relative time, right? Now what about the burst time? 9, 4, 5, 7 and 3. This is the burst time. Now we have to give some priority to the processes. So the priorities will be given by the CPU itself. So five, 3, 1, 2, 4 priorities, right? 5 for P1, 3 for P2, 1 is for P3, 2 is for P4, 4 is for P5. Here I am taking 1 as or low in number is having high priority. Low in number in high priority. And also the mode is non-preemptive mode. Non-preemptive. So as I said that non-preemptive means we should not disturb the process which is going on execution by the CPU, right? So until it completes its execution, no other process should enter into the running state. Now let us prepare the Gantt chart so that we can find out all these times. So this is the Gantt chart. Gantt chart. So always this starts from 0. At the 0 arrival time, only one process is in ready queue. So even though the priorities, see here the priorities. So 5, 3, 1, 2, 4. So here the highest priority is given to the process 3. But process 3 is arrived at 2, arrival time 2. So initially only one process is available in ready state. So this process will be allocated to the CPU. Right? So it will be allocated till 9, and then So after arrival 9, all these processes are available in ready queue. So because P2 arrived in 1, P3 arrived in 2, P4 arrived at 3, P5 arrived at 4. So here it is already 9. So all these processes will be available in ready queue. So among all these processes, which one is having the highest priority? That is low in number, P3. So now P3 is allocated to the CPU and it will be executed till 5. So 14. Now P1 is completed, P3 is completed. Now what about the remaining? At the time 14, now 3 processes are available in ready queue, P2, P4, P5. So among these 3 processes, so which one is having the high priority? This one, P4 with a 2, right? Low in number, high priority, 2. So P4 will be given to the CPU and it will be executed till 21 because it requires 7 milliseconds to complete its execution. Right? This one completed. Now at the time 21, 2 processes are available in ready queue, P2 and P5. So among these two, P2 is having highest priority because 3. Here P5 is having 4. So lowest number is high priority. So P2 is having high priority. P2 will be given to the CPU. It will be executed till 25. Right? Next, automatically P5, 4. So P5 is given to the CPU and it will be executed till 28. Hope you understood. So at the time of 0, only one process is available. So we need not check for the priority. So automatically P1 is allocated to the CPU. So it is not a non-preemptive. This implementation is a non-preemptive algorithm. So it is a non-preemptive means we should not interrupt the process during its execution. So we have to let it finish its execution. So after completion of this execution, the next process with the higher priority should be allocated to the CPU. So at the time 9, there are 4 processes available, P2, P3, P4, P5. So among these 4 processes, P3 is having the lower priority because low in number, high priority. So low number, so it is having the highest priority. So P3 is allocated, and then after completion of P3, 3 processes are available. Among these 3, P4 is having the highest priority with number 2. So P4 is executed, then P2 and P5. So if you sum all these things, we should get the 28. So 9 plus 4, it's 13, 18, 25 and 28. So this Gantt chart is correct, right? Because the total time required to complete all these processes is 28. Completion time. So P1 completed at 9, P2 completed at 25, P3 completed at 14, P4 completed at 21, P5 completed at 28. Right? Now turnaround time, as I said, that turnaround time is a completion time minus arrival time. So 9 minus 0, it's 9, 25 minus 1, it's 24, 14 minus 2, it's 12, 21 minus 3 is 18, 28 minus 4 is 24. Right? So this turnaround time is completion time minus arrival time. Similarly, waiting time is equal to turnaround time minus burst time. Right? Now, waiting time. So P1 arrived at 0. Here, P1 is allocated to CPU at 0, arrived at 0. So 0 minus 0, 0. Next, P2. P2 is allocated to CPU at 21 and arrived at 1. So 21 minus 1, it's 20. So based upon the formula also you can check 24 minus 4, it's 20. Next, P3. P3 is allocated to CPU at 9. P3 is allotted at arrival time is 2. So 9 minus 2, it's a 7. 12 minus 5, it's 7. Next, P4. P4 allocates the, P4 is allocated to the CPU at 14, arrived at 3. So 14 minus 3, it's 11. So 18 minus 7, it's 11. Next, P5. P5 is allocated to the CPU at time 25 and arrived at 4. So 25 minus 4 is 21. Right, 21. So 24 minus 3 is 21. Hope you understood this one. So calculate the average, total all these things. So you will get the total turnaround time. Total turnaround time. So see 9 plus 24, 33. 33 plus 12, 45. 45 plus 18, 63. 63 plus 24, 87. So average turnaround time is equal to 87 divided by how many processes are there? 5 processes are there. This is the average turnaround time. Now waiting time, 20 plus 7, 27, 38, 59. So here the average waiting time is equal to 59 by 5. This is the average waiting time. Okay, so hope you understood. Here some priorities will be given to the process. When based upon those priorities, we have to allocate the process to the CPU. So as it is a non-preemptive mode, so we should not disturb the process which is going on executing by the CPU. So once completion of that process, the next process with the highest priority will be allocated to the CPU. Right? Hope you understood this one. So let us take one more example so that your doubts will be clarified. See, now let us take the 4 processes, P1, P2, P3, P4. So with arrival times 0, 3, 4, 9. With the burst times 60, 30, 40, 10. What's the priority? 3, 2, 1 and 4. Right? So P1 is having 3, P2 is having 2, P3 is having 1, P4 is having 4. So now among these processes, which one is having highest priority? P3. So P3, then the second highest priority P2, next third priority P1, fourth priority P4. But here at the time of 0, only one process is available in ready queue, that is P1. So, which is having the third priority. Even though only one process is available in CPU, first P1 will be get executed by the CPU. Right? Let us prepare the Gantt chart. So 0, first P1 will be allocated to the CPU. So until 60. So at the time of 60, all the processes are available in ready queue. Among these 3 processes, which one is having the highest priority? This one, P3, because it is having 1. That means lower number will be highest priority. So P3 is having the highest priority. No, P3 will be allocated to the CPU and it will be executed until 40. So it's 100. Next, 2 processes are available in ready queue. At the time of 100, 2 processes are available in ready queue. So P2 is having with 2 priority, P4 is having with 4 priority. So as P2 is having with the highest priority, P2 should be allocated to the CPU. So now P2 is allocated to the CPU, it runs until 130. Right? After that, only one process is remaining, that is P4, it is allocated, and now till 140 it will be available. So let us find out the total. 60 plus 30, 90, 90 plus 40, 130 and 140. So here also 140. Now this Gantt chart is correct because so the total time required to complete executing all the processes is 140. So here also it's 140. Now completion time. So P1 is completed at 60, P2 is completed at 130, P3 is completed at 100, P4 completed at 140. Turnaround time. Turnaround time is completion time minus arrival time. So 60 minus 0, it's 60. 130 minus 3, 127. 100 minus 4, it's 96. 140 minus 9, it's 131. Right? Now waiting time. So waiting time is turnaround time minus BT. So turnaround time minus BT. 0. 127 minus 30. 97. 96 minus 40. 56. 131 minus 10. 121. So we can observe here also by using the Gantt chart also we can find out the waiting time. So P1 allocates to the CPU at 0, arrived at 0. So 0. Next P2 is allocated to the CPU at 100, arrived at 3. So 100 minus 3 is 97. So 97. P3 is allocated to the CPU at 60 and arrived at 4. 60 minus 4, 56. P4 is allocated to the CPU at 130 and arrived at 9. So 130 minus 9, 121. So this is the correct one. Now we can find out the average waiting time and average turnaround time. So that by adding all these things divided by 4. So total divided by total turnaround time divided by 4. So average turnaround time. Similarly, average waiting time is equal to total waiting time by 4. So hope you understood this simple thing. So this is a priority scheduling algorithm. The name itself indicates we have to give some priority to all the processes, and based upon the priority the process will be allocated to the CPU. So here the low in number is having the highest priority. So in some examples we can say high in number is having the highest priority. So based upon that situation, based upon that case, based upon the given note, so we have to solve the problem. And also this is a non-preemptive. If one process is going to be executed by the CPU, so until it completes its execution, no other process should be entered into the running state. So that means no interruption. There must be no interruption. Right? So hope you understood this simple algorithm. That is a priority scheduling algorithm in preemptive mode. So priority scheduling algorithm. So here mode is preemptive. So there will be an interruption. And low in number is having highest priority. Right? So let us see the procedure by taking one example. So let us consider here the priority, process ID, arrival time, burst time, so time taken to complete its execution, completion time, turn around time, and waiting time. Right? So we have to consider the processes, arrival time, burst time, as well as the priority, and based upon this we have to prepare the Gantt chart, and from that Gantt chart we have to find the completion time of each process, turnaround time of each process, as well as the waiting time of each process. Now let us take an example. 4 processes P1, P2, P3 and P4. So the arrival time is 0, 2, 3 and 5, and the burst time is 10, 5, 2, 20. The burst time is 10, 5, 2, 20. Now the priority is 2, 1, 0, 3. So here 4 processes, we have taken the 4 processes, their arrival time and burst time and their priority. So in this example, we can say that P3 is having the highest priority, then P2 is having the highest priority, then P1 is having the highest priority, then P4 is having the highest priority. So among the 4 processes, P3, P2, P1, P4, based upon the priority, right? Now let us prepare the Gantt chart. Gantt chart. See, at the time 0, at the arrival time 0, only one process is available in ready queue, so P1 is allocated to CPU. So at time 1, no other process had entered into CPU. At time 2, P2 entered into CPU, which is having the highest priority than P1. Okay, don't get confused. So until the time 2, no other process is available in ready queue. Only one process is available. So P1 is allocated to CPU, so it completes its time in 2, so it will be 8 now. So at the time 2, P2 is available in ready queue. So P2 is having highest priority 1 than P1. So P2 is allocated to CPU. Now at the time 3, one more process is available in ready queue. So now what are the processes are available in ready queue? P3 and P1, right? So P3 is having highest priority than P1, and also P3 is having highest priority than P2. So P2 will be again moved back to the ready state. So how much time? So here 1 second is completed. Now P3 is allocated to CPU. At the time of 5, okay, it executes till 5, and at the time of 5, one more process is available, P4, which is having the low priority than P3. Okay, here P4 is having the low priority than P3. So P3 continues its execution until it completes the execution. So P3 means 2, that means 5. At the time of 5, it's completed, right? P3 completes. Now at the time of 5, what are the available processes? P4, P2, P1. Okay, P3 already completed, so P4, P2, P1. Among these, which one is having the highest priority? P2 is having the highest priority. So P1 is having 2, P2 is having 1, P4 is having 3. So here low in number is having high priority. So 1 is the highest priority. So P2 is having highest priority. Now P2 is allocated to the CPU. So P2 completes its execution. So 4. So 9. So it becomes 0. Now at the time of 9, so P2 completes. At the time of 9, P1 is available and P4 is available. So among these two, which one is having the highest priority? P1 is having the priority 2, P4 is having the priority 3. So low in number is having the highest priority. So P2 is having highest priority. So P1 will be allocated to the CPU and it completes its execution, total 8, that is 17. Right? At the time of 17, only one process is available, that is P4. Now P4 is allocated to the CPU and it completes its execution till 37. So it becomes 0. So it becomes 0 in the earlier. Now it becomes 0. Right? So hope you understood this one. So I will erase all these things. Only burst time I will be displaying. So for better understanding, I am writing all these things. So erase these things. Right. Now completion time for this one is P1 completed at 17, P2 completes at 9, P3 completes at 5, P4 completes at 37. Right? 17, 9, 5 and 37. Now turnaround time. So as we know that turnaround time is the completion time minus arrival time. Similarly, waiting time is turnaround time minus burst time. So we have to remember these formulas. So CT minus arrival time. So 17, 9 minus 2 it's a 7, 5 minus 3 it's a 2, 37 minus 5 it's a 32. 17, 7, 2, 32. Now waiting time. So waiting time can be calculated by using this formula or by using this Gantt chart also we can find out the waiting time. So first let us write this formula. Based upon the formula we will write down and I will explain. 17 minus 10, 7, 7 minus 5 it's 2, 2 minus 2 it's 0, 32 minus 20 it's 12. Now let us check with the Gantt chart. So P1. So P1 allocates the CPU at 9 and previously it completes 2. So 9 minus 2, 7. So 7 and arrived at 0. So 7 minus 0, 7. Next coming to the P2. P2 is allocated to CPU at 5 and earlier 1 second is completed. So 5 minus 1, 4 and arrival time is 2. 4 minus 2, 2. Next P3. P3 allocated to the CPU at 3 and arrived at 3. So 3 minus 3, 0. There is no waiting time. Next P4. So P4 enter into the CPU at 17 and arrived at 5. So 17 minus 5 is 12. So by calculating this average, so 17 plus 7, 24, 26, 58 divided by 4. So as there are 4 processes, so this is average turnaround time. And here also 7 plus 2, 9, 9 plus 12, 21 divided by 4. This is average waiting time. So average waiting time. So hope you understood this one. So here, so first process is allocated to the CPU and based upon the arrival time and the priority, the process will be again shifted to the ready state and the highest priority process is allocated to the CPU. Right? So there is an interruption here. So that's why we call it as a preemptive priority scheduling algorithm. And here low in number is having the highest priority. So if you count this burst time, 20 plus 2, 22, 22 plus 5, 27, 37. So the time required to complete executing all these processes 37. So in the Gantt chart also we got 37. Right? So hope you understood this one. Let us solve one more example so that you can get a more idea about this priority scheduling algorithm in a preemptive mode. Now let us take one more example. So my main concentration is for the slow learners. So if I solve more examples, automatically their doubts will be get clarified and they will be easily understood, right? So don't think otherwise. Now coming to the second one, let us take 5 processes. P1, P2, P3, P4, P5 and the arrival time is 0, 1, 2, 3, 4 and the burst time is 9, 4, 5, 7, 3 and the priority is 5, 3, 1, 2, 4. Right? So P1 is having 5, P2 is having 3, P3 is having 1, P4 is having 2, P5 is having 4. Now before going to the arrival time and burst time, first let us see which process is having the highest priority. So as we know that low number highest priority. So first P3 is having the highest priority, then P4 is having the highest priority, then P2 is having the highest priority, then P5 is having the highest priority, and at last P1 is having the highest priority. So this is the highest priority to lowest priority, high to low, right? So that other than arrival time and burst time and all these things, just we are writing according to the priorities, right? Now let us draw the Gantt chart so that we can find all those things. Gantt chart. So always starts from 0. So at the arrival time 0, only one process is available. So P1 is allocated. So at the arrival time 1, another process is available, P2, which is having the highest priority than P1. So P1 is having 5, P2 is having 3. So P2 is having the highest priority than P1. So P1 sent back to the ready state and P2 will be allocated to the CPU. Right? So after at the time 2, again, so here 8, here 3. So because 1 second completed, here also 1 second completed. Now at the time 2, P3 is in ready state, which is having the priority 1. That means highest priority than P2 and P1. So P3 is allocated to the CPU, right? So at the time 3, again it checks for P4, which is having the low priority than P3. Low priority than P3. So P3 executes, and now at the time 4, P5 is already in ready queue, so which is having the again low priority than P3. So P3 continues its execution until it completes its execution. So 7. So it becomes 0. Right? Now at the time 7, 4 processes are available in ready queue. P1, P2, P4 and P5. So among these 4, which one is having the highest priority? P4 with 2, that is low in number, higher priority. So P4 is having a low number, that is highest priority. So P4 is allocated to CPU and it completes its execution 14. Next, so this becomes 0, so P4 completed. Now at time 14, P5 is available, P2 is available, P1 is available. Among these 3, P2 is having highest priority because P1 is having 5, P2 is having 3, P5 is having 4. So among these, lower number is for P2, low number is high priority. So P2 will be allocated to the CPU and it completes its execution. So P2 is having still 3 seconds to complete its execution. So it completes its execution. Next, at time 17, again we had 2 processes in ready queue, 5 and 4. Among these 2, 4 is having the highest priority. So P5 is allocated to the CPU and it completes its execution. So 3, so 20. Right? Next, at time 20, only one process is available in ready queue, that is P1. Now P1 is allocated to CPU and it completes its execution, that is 28. This becomes 0. P1 completes. So hope you understood, right? At the time 0, only one process is available, so directly that process is allocated to the CPU. So it executes until 1 second, so until the arrival time becomes 2. At the arrival time becomes 2, there is a, sorry, at the arrival time becomes 1, another process is available which is having the highest priority than P1. So P1 is removed from the CPU and P2 is allocated to CPU. And again P2 is executed. At the time arrival time 2, another process is available in ready queue which is having the highest priority than P2. Now P3 is removed from the CPU and P3 is allocated to the CPU. And at the time 3, P4 is available in ready queue which is having the low priority than P3. So P3 continues its execution. At the time 4, P5 is available in ready queue which is having again low priority than P3. So P3 still continues its execution until it completes its execution. So after that, at time 7, we are having 4 processes, 4 processes available in ready queue, P1, P2, P4, P5. Among those 4, P4 is having the highest priority, P4 is allocated to the CPU and it gets executed till it completes its execution. And after the 14, 3 processes are available. Among those, P2 is having the highest priority. So P2 is allocated to the CPU and it completes its execution. And at the time 17, 2 processes are available in ready queue. Among these 2, P5 is having the highest priority. P5 is allocated to the CPU and it continues its execution. And finally, P1 is having the highest priority. Only 1 process is remaining, so P1 is allocated to the CPU and it completes its execution. Hope you understood this Gantt chart. So if you are able to write this Gantt chart correctly, automatically we can find all these things, right? So I will erase all these things except the burst time. See, what is the total time required? 9 plus 4, 13, 18, 28. See, here also it requires total 28 milliseconds to complete all the processes to get executed. Now completion time, let us write the completion time. So P1 is completed at 28, P2 is completed at 17, P3 is completed at 7, P4 completes its execution at 14, P5 completes its execution at 20. Right? This is the completion time for each process. Now turnaround time. So as we have said, that turnaround time is equal to completion time minus arrival time. Waiting time is equal to turnaround time minus burst time. So this is the formula. So turnaround time, completion time minus arrival time. 28 minus 0, 28. 17 minus 1, 16. 7 minus 2, it's 5. 14 minus 3, it's 11. 20 minus 4, it's 16. Next, waiting time. So waiting time, turnaround time minus burst time. 28 minus 9, it's 19. 16 minus 4, it's 12. 5 minus 5, it's 0. 11 minus 7, it's 4. 16 minus 3, it's 13. Now let us check with the Gantt chart. So coming to the P1, so P1 enters the CPU at 20 and already completes its execution for 1 second. So 20 minus 1, 19. Arrived into the ready queue at 0. So 19 minus 0, 19. Next, P2. P2 allocated to the CPU at 14. So in the earlier only 1 second is completed. So 14 minus 1, 13. 13 minus it arrived into ready queue at 1. So 13 minus 1, 12. Next, P3. P3 is allocated to the CPU at time 2 and P3 is arrival time is 2. So 2 minus 2, 0. Next, P4. P4 allocated to the CPU at time 7 and it is arrived at 3. So 7 minus 3, it's a 4. P5. P5 is allocated to the CPU at 17 and it is arrived at 4. 17 minus 4, it's a 13. So average turnaround time is equal to 28, 16. So 44, 49, 60, 76. 76 by how many processes? 5 processes. 76 by 5. Now average waiting time. So 19 plus 12 is 31, 35 plus 48. 48 by 5. Average waiting time. Right? Hope you understood. Here this is the process for preemption. Preemptive priority scheduling algorithm. Right? So preemption means there will be interruption. So whatever the process is in running state, so if any other process is available with a highest priority than the running process, automatically the running process will be sent back to the ready state and the new process, that is which is having the highest priority process, will be allocated to the CPU. Right? So this is the process of preemptive priority scheduling, round robin scheduling algorithm. So here we have to consider some time quantum, and based upon the time quantum the CPU will be allocated to the processes. Right? So every process will be allocated to the particular time quantum itself, and after completion of the time quantum the process will be removed from the CPU and it will be again sent to the ready queue, and that process should wait until it gets its turn to complete its execution. So every process will be having the equal time quantum. That means every process will spend equal time with the CPU to complete its execution. So let us see an example. So here there are two modes. One is considering the arrival time and without considering the arrival time. Now let us look with the time quantum and arrival time. Let us see an example. So time quantum plus arrival time. So we are considering both time quantum and arrival time. We are considering both here. So let us take this process arrival time, burst time, completion time, turn around time, waiting time. So we have to find out all those things. So let us take an example. So let us take complete 4 processes, and the arrival time for this process 0, 1, 2, 4. The burst time 5, 4, 2 and 1. So let us find out this completion time, turnaround time and waiting time. So for this we have to prepare 2 boxes, that is, one is for ready queue and another one is for this Gantt chart. Now, so let us take the time quantum is equal to 2 milliseconds. Here the time quantum is 2 milliseconds. Now let us take the ready queue. So this is the ready queue and we have to follow this ready queue, right? To allocate the process to the CPU, we have to follow this ready queue. So this is the ready queue and this is the Gantt chart. This is the Gantt chart, right? So as we know, at the time of arrival time, at the time of 0, P1 is in the ready queue, right? P1 is available in the ready queue. So at the time, so only P1 is available, so P1 will be removed from the ready queue and it will be allocated to the CPU and it will be get executed. Here the time quantum is 2, so P1 spends only 2 milliseconds with the CPU, so 2, right? So the remaining is 3. So here P1 still requires 3 milliseconds to complete its execution. Now after completion of 2, that means after completion of time quantum, P1 is removed from this ready queue and P1 is removed from the CPU and it will be sent to the ready queue. Before that, at the time of 2, there are 2 processes available in ready queue, that is P2 and P3. See, at the time of 2, there are two processes in the ready queue, P2 and P3. And after completion of this 2 milliseconds, P1 will be removed from the CPU and is allocated to the, it will be moved to the ready queue. So P1, right? So understood? So first at the time 0, only P1 is available in the ready queue. It will be removed from the ready queue and it will be allocated to the CPU. So after completion this execution to 2 milliseconds, at the time of 2 more processes are available in the ready queue. So after completion of this time quantum, P1 will be removed from the CPU and it will be sent to the ready queue. Now we have to allocate the CPU according to the order of processes available in ready queue. Now P2 is removed from the ready queue and allocated to the CPU. Again, all the processes will be executed only with an equal time quantum, that is only 2. So P2 will also execute only 2 milliseconds. So still P2 requires 2 milliseconds to complete its execution, right? So at the time of P4, at the time of 4, P4 is also available in ready queue, right? P4 is also available in ready queue. Now after completion of time quantum, P2 still requires 2 milliseconds, so P2 is removed from the CPU and it will be moved to the ready queue. So here P2, right? Next, be removed from the ready queue. P3 is allocated, right, to the CPU and it will be executed 2 milliseconds. So P3 completes its execution. So it completed its execution. So P3 doesn't require the CPU once again, right? So within the given time quantum, P3 completes its execution. Next, P1. So P1, again the time quantum is 2, so 8. So it still requires 1 milliseconds to complete its execution. So P1 will be removed from the CPU. So at the time of 8, no other processes are available in ready queue. So P1 will be removed from the CPU and it will be added in the ready queue. So P1. Now P4. So P4 is allocated to the CPU and it executes only 1 second. So even though the time quantum is 2, it requires only 1 second to complete its execution. So it will be 0. Right? Now P2. P2 is allocated. That is also for 2 milliseconds. 0. So P2 completes its execution and then P1 completes its execution with only 1 second, that is 12. Right? So this is the order or this is the procedure to be followed for executing the round robin scheduling algorithm. So first, at the time of 0, P1 is allocated to the CPU and it will be executed for 2 milliseconds. And at the time of 2 more processes are available in ready queue, P2 and P3. And still P1 requires 3 milliseconds to complete its execution. So P1 is removed from the CPU and P1 will be allocated to the, P1 will be moved to the ready queue. And P2, in the order of ready queue, P2 is available. So P2 will be allocated to the CPU and it will again executes 2 milliseconds, so 2 to 4, and it still requires 2 milliseconds. At the time of 4, P4 is also available in ready queue, so P4, and it still requires 2 milliseconds, so P2 will be removed from the CPU and added to the ready queue. And in the order, again next P3 will be executed for 2 milliseconds, and within this time quantum itself, it completes its execution. So P3 will not be added to the ready queue because it completes its execution. Next, after that, in the ready queue, P1 is available. So P1 is removed from the ready queue and it will be allocated to the CPU and it will be executed for 2 milliseconds and still it requires 1 milliseconds. So P1 will be again added to the CPU, ready queue. Next, in the order, P4 is available in the ready queue. So P4 will be removed from the ready queue and it will be allocated to the CPU and it again, the P4 requires only 1 millisecond to be executed. So P4 is executed till 1 milliseconds and completes its execution. So it doesn't require any other another time to complete its execution. So P4 will not be added to the ready queue. So now in the order, P2 is available in the ready queue. So P2 will be removed from the ready queue and allocated to the CPU. So P2 requires 2 milliseconds and here the time quantum also 2 milliseconds. So it completes its execution at this level. And then in the order, P1 is added in the ready queue. So P1 will be allocated to the CPU and it executes 1 millisecond and it completes its execution. So this is the Gantt chart and this is the ready queue. So hope you understood this thing, right? So 5, 4, 2, 1. Now completion time. See here the completion time. So completion time of P1 is 12. Completion of time of P2 is 11. Completion time of P3 is 6. The completion time of P4 is 9. Turnaround time means completion time minus arrival time. 12 minus 0, 12, 11 minus 1, it's 10. 6 minus 2, it's 4. 9 minus 4, it's 5. Waiting time, that is turnaround time minus burst time. 12 minus 5, it's 7. 10 minus 4, it's 6. 4 minus 2, it's 2. 5 minus 1, it's 4. So you can also check with the waiting time with this Gantt chart. So P1, here 11. 11 minus 2, 9. 9 minus 2, 7. Right. Next P2, coming to the P2, it's 9. 9 minus 2, 7. And it arrived at 1. So 7 minus 1, 6. Next P3, 4, it arrives at 2, so 4 minus 2 it's 2. Next P4, 8, it arrives at 4, 8 minus 4 it's 4, right? So find out this one, so 19, so average waiting time is 19 divided by 4. So like this way we can use this, you can implement this round robin scheduling algorithm. So here the main thing is time quantum, and another one is based upon the arrival time. So if the arrival time is not given, so we can consider the arrival time for all the processes 0. So, and we can, let us see one more example for this round robin algorithm. So here I have considered 5 cases, 5 processes, and with the arrival times 0, 1, 2, 3, 4, and the burst time, so 8 milliseconds to complete the execution of P1, 1 for P2, 3 for P3, 2 for P4, and 6 for P5. And here let us consider the time quantum as 3 milliseconds. The time quantum as 3 milliseconds. Now let us draw the ready queue and Gantt chart. See, this is the ready queue. This is the Gantt chart, right? So at the time of 0, only P1 is available in the ready queue. So P1 is available in the ready queue. So this P1 will be removed from here and it will be allocated to the CPU and it will be executed till 3 milliseconds. So P1 still requires 5 milliseconds to complete its execution. So at the time of 3, right? At the time of 3, P2, P3, P4 is also available in ready queue. So P2, P3, P4 is also available in ready queue at the time of 3. Now, after completion of this time quantum, P1 still requires 5 milliseconds to get executed. So P1 will be removed from the CPU and it will be allocated, added in the ready queue. Right? Now, in the order, now P2 will be removed from the ready queue and it will be allocated to the CPU. Now P2 executes its execution till only 1 millisecond because only 1 second is required to complete its execution. So P2. Next, at the time of 4, P5 is also available in ready queue. So P5 is available in ready queue. Right? So next in the order, P3 is removed from the ready queue and it will be allocated to the CPU. And again P3, it requires 3, so 3 milliseconds it will be executed. Right? So P3 doesn't require any more allocation of CPU. Right? So P3 will not be added again to the ready queue because it completes its execution. Now in the order P4, the P4 is removed from the ready queue. It will be added to the CPU, allocated to the CPU, and it executes 2 milliseconds. 0 because here it is a time quantum is 3, only 2 milliseconds are required to complete its execution. Right? Now next, after completion of P4, P1 is executed, so it will be removed from the ready queue, it will be allocated to the CPU, and again 3 milliseconds, it will execute 3 milliseconds. Now again it requires 2 milliseconds to complete its execution, so P1 will be removed from the CPU and it will be added to the ready queue. Now P5, in the order P5, remove the P5 from the ready queue and it will be allocated to the CPU, and now P5 is also executes to 3 milliseconds, so 3 milliseconds. So again P5 requires 3 milliseconds to get executed, so P5 is removed from the CPU and it will be moved to the ready queue. Now in the order P1 removes from the ready queue, P1 is allocated to the CPU, so P1 again still it will be executed till 2 milliseconds. So after 2 milliseconds P1 completes its execution. Now in the ready queue, P5 is there, so P5 is removed from the ready queue, P5 is allocated to the CPU and it executes 3 milliseconds. So it is also completed its execution. So all the processes have completed its execution. Right? So this is the ready queue and this is the Gantt chart. So at the time of 0, P1 is available in the ready queue, so P1 will be allocated to the CPU, and here the time quantum is 3, so P1 is executes only 3 milliseconds. At the time of 3, these 3 processes are available in the ready queue, so P2, P3, P4 is added in the ready queue. So after completion of this time quantum, P1 still requires 5 milliseconds to get its execution, so P1 will be added in the ready queue. So now in the order, P2 will be removed from the ready queue and it will be executed only 1 millisecond, so it requires only 1 milliseconds to complete its execution, so it completes its execution till from 3 to 4. Now in the order, P3 will be there, so P3 will be removed from the ready queue and it will be allocated to the CPU and it executes 3 milliseconds to complete its execution, so it executes from 4 to 7 as the time quantum is also equal to 3. So P3 completes its execution. Now in the order, P4 is available in the ready queue, so P4 will be available, removed from the ready queue and it will be allocated to the CPU and it executes 2 milliseconds to complete its execution. So from 7 to 9 it will complete its execution. Next in the order, P1 will be there in the ready queue, so P1 will be removed from the ready queue and it will be added to the CPU, and again P1 will execute till 3 milliseconds because time quantum is 3. So again still P1 requires 2 more milliseconds to complete its execution, so P1 will be removed from the CPU and it will be added in the ready queue. So in the order, P5 is there, so P5 will be removed from the ready queue and it will be executed, allocated to the CPU and it executes for 3 milliseconds as the time quantum is 3. So it still requires 3 milliseconds to complete its execution, so P5 again it will be removed from the CPU and it will be added in the ready queue. So in the order, P1 is there, so P1 is removed from the ready queue and it will be allocated to the CPU and it executes 2 milliseconds to complete its execution, so it executes from 15 to 17 and it completes its execution. So in the order, P5 will be there, so P5 will be removed from the ready queue and it will be allocated to the CPU and it executes 3 milliseconds which completes its execution. So from 17 to 20 it will be this P5 will be executed. So this is the process. The scheduler will scheduling these processes according to the time quantum and arrival time. Now see, add all these things, 8 plus 4 9, 9 plus 3 12, 12 plus 2 14, 14 plus 6 20. So Gantt chart is also 20. So 20 milliseconds are required to complete the execution of all the processes. Right? Now completion time. P1 completes at 17, P2 completes at 4, P3 completes at 7, P4 completes at 9, P5 completes at 20. Next, turnaround time. It's a completion time minus arrival time. 17 minus 0 it's a 17, 4 minus 1 it's a 3, 7 minus 2 it's a 5, 9 minus 3 it's a 6, 20 minus 4 it's a 16. Now waiting time. Turnaround time minus burst time. 17 minus 8 it's 9, 3 minus 1 it's 2, 5 minus 3 it's 2, 6 minus 2 it's 4, 16 minus 6 it's 10. So let us check this waiting time with the Gantt chart. So P1, so here P1 is a 15, here 3, P1 15 minus 3 is a 12, 12 minus 3 is a 9, 9 and arrived at 0, so 9 minus 0 it's 9. Next, P2, P2 3, arrived at 1, so 3 minus 1 is 2. Next, P3, it's 4, 4 minus arrived time it arrived at 2, so 4 minus 2, 2. Next, P4, so P4 is allocated to the CPU at time 7, it arrived at 3, so 7 minus 3, 4 milliseconds it has been waited. Next, P5, so the CPU allocated to the CPU, P5 is 17 and previously 3 milliseconds completed, so 17 minus 3 is a 14, so 14 and arrived at 4, so 14 minus 4 is 10. Hope you understood this one. So find out this total turnaround time and waiting time. From that we can get the average turnaround time and average waiting time. Right? So hope you understood this simple procedure. So don't get confused. So if you really understood and if you really feel my videos are useful to you, like my videos and share my videos with your friends, and don't forget to subscribe to our channel. And if you are having any doubts regarding this scheduling algorithms, feel free to post your doubts in the comment section so that I will definitely try to clarify all your doubts. So thanks for listening, and don't forget to subscribe to our channel. So keep following my sessions. Thank you very much.